So when we were working with Taylor polynomials, as we took more and more terms, then the approximation became more and more accurate. So why not just take an infinite number of terms? And then the Taylor polynomial becomes an infinite series called a Taylor series. And a Taylor series is a type of power series because, it has the variable x in it. And it turns out if we can find any power series representation for a function, then it's the same thing as the Taylor series on that interval. So a Taylor series centered at c, some number, has the general form of this. We start the index at 0, and we have the value of the nth derivative of the function at c over n factorial times x minus c to the n power. And as you can see, the expansion just looks like a Taylor polynomial, but it goes to infinity. And in the special case when c equals 0, then it's called a Maclaurin series. And so there are 3 Maclaurin series that you have to memorize. And those are e to the x, sine of x, and cosine of x. So to find the Maclaurin series, we're just going to write out a few terms of the Maclaurin polynomial, manually, and then find a general term. So for e to the x, of course, all the derivatives are just e to the x too. And so at x equals 0, all of the derivatives are equal to 1. So the Maclaurin series is pretty simple. And we can find a general term as x to the n over n factorial, starting at n equals 0. And of course we want to find on what interval is this Maclaurin series a valid approximation. So we use the ratio test on this power series. And this limit is always going to be equal to 0. So the interval of convergence is infinite, and we have this power series is the Maclaurin series for e to the x for all values of x. So for sine of x now, the derivatives are going to alternate between 0, 1, and negative 1. Now since whenever it's sine of x, it's going to be 0. So you can see when we make the Maclaurin polynomial, all we have is the odd powers of x. Everything else is going to be 0. So you can find a general term. It's going to be an alternating series, negative 1 to the n power times x to the 2n plus 1 over 2n plus 1 factorial. So again, we use the ratio test to determine the interval of convergence for this power series. And again, this limit turns out to always be 0. So again, the interval of convergence for this power series of sine of x is infinite. And then for cosine, we can either do it by hand, and you'll find that you only have the even powers of x instead of the odd powers like in sine of x. Or you can just differentiate this power series for sine x, because of course cosine of x is the derivative of sine x. So differentiating this Maclaurin series, we bring down the 2n plus 1, subtract 1 from the power, and then we can rewrite 2n plus 1 factorial as 2n plus 1 times 2n factorial. That allows us to cancel out the 2n plus 1. And then we just have negative 1 to the n, again as an alternating series, times x to the 2n over 2n factorial. And remember, when we differentiate or integrate a power series, the radius of convergence stays the same. So this Maclaurin series for cosine x has an infinite radius of convergence.